Now we begin our final chapter for this course. We're going to discuss intermolecular forces, and we'll discuss liquids, solids, and phase changes. But we're going to start off with a quick video. So just quick disclosure, I don't have any stock in Ultra Ever Dry, but that's a fun, entertaining video showing what super hydrophobic materials and super oleophobic materials do. And they look kind of magical compared to our normal experiences when liquids normally wet solids and surfaces. And it turns out all this is driven by intermolecular forces. And so let's look and see what an intra versus an intermolecular force looks like. Just so you know, all semester long, we've worked with intramolecular forces. That is, forces within a molecule, covalent bonds, ionic bonds, and looking at electrons around atoms and how they might share those with other atoms. An intermolecular force is a force between molecules, and it is typically a much weaker force. But there are many more of those forces, and as such, they can dictate the properties of a material to a very large extent. Now, the strength of the intermolecular force will very often be driven by the three-dimensional structure and the intramolecular forces within a molecule. And we'll see that in a little bit. So what we're doing is we're tying our first thoughts on making Lewis dot structures to be a CPR, getting shapes of molecules and hybrid orbitals, and now we can take those concepts and determine what are the intermolecular forces operating in a material. So we'll start off and we'll look at an overview of physical states and phase changes. This is something we just briefly touched on much earlier, but now we'll go into the depth that we need to cover. It'll turn out we'll see that these physical states and phase changes are driven by intermolecular forces. Then we'll look at the types of intermolecular forces that exist. We'll look at some quantitative aspects of phase changes. We'll look at the liquid state, and then we'll go into water and some of its special properties. So first, we have the two big types of attractive forces. There's intramolecular forces, or bonding forces, which are found within a molecule. The chemical behavior, that is the reactivity of a substance, is the same regardless of the phase, because the same constituent particles are present in each case. So water molecules are present whether the substance is a solid, liquid, or gas. And so we'll see that the reactivity of water would be the same in all three of those phases. The speed of the reaction can change, and some other things can change, but the intrinsic chemical nature will be similar. Intermolecular or non-bonding forces are found between molecules. And the physical behavior of each phase of matter is different because kinetic energies of the molecules are sufficient to disrupt these weaker intermolecular forces and change their manifestation. Intermolecular forces now, the forces between different molecules, arise from the attraction between molecules with partial charges or between ions and molecules. And what we mean by partial charges here are, for example, if you have HF. HF has a dipole moment on it. There's a partial charge on the fluorine and there's a partial charge on the hydrogen. Those partial charges affect the area surrounding the molecule, and this gives rise to intermolecular forces. Intermolecular forces are relatively weak, though, compared to bonding forces, because they're smaller charges, they're partial charges, and they are farther apart. That is, the distance between molecules is greater than the bonding distances that we've looked at thus far. Intermolecular forces and their magnitudes affect many bulk properties of materials, and these include, but are not limited to, phase transitions, that is, the boiling and melting points and the enthalpies of boiling and melting, the surface tension of liquids, just like we saw in that superhydrophobic system, the ultra-dry commercial that we watched. Solvent, gas, and solid solubilities are all dependent on intermolecular forces. Capillary action, viscosity of liquids, and other interesting So as we look at this, the first question we have is, the distances are further. Well, what do these distances look like? We've learned about atomic radius. We've learned about ionic radius. We've learned what a covalent radius is. So you know all three of those. You've learned those from your chapters 8 through 11. Now we're going to look at something called the van der Waals radius. The van der Waals radius is the distance between two non-bonded atoms in different or adjacent molecules. So different molecules now that come up next to one another, they have a van der Waals distance. And that van der Waals distance then can be converted to a van der Waals radius, right? We just divide, when we had a covalent radius, it was just half the covalent distance. The van der Waals radius is 1/2 of the closest distance between the nuclei of two non-bonded atoms, that is, two atoms in different molecules. The van der Waals radius is always larger than the covalent radius. Here are some trends in covalent and van der Waals radii for a number of the main group atoms. And you can see in blue is the covalent radius. So those are typically small numbers in picometers. And then we can see the much larger numbers, the red numbers, are the van der Waals radii. And they can be at least 2 times bigger in many cases than the covalent radius. So what does that mean? You have a larger van der Waals radius. That means that the atoms are further apart, so their interactions are necessarily weaker, which helps us understand why intermolecular forces are weaker than intramolecular forces. So now we can see what this looks like. Here are the 3 forces that we have discussed thus far. These are the intramolecular forces, these 3: ionic, covalent, and metallic forces. Ionic forces are involved in ionic bonding, right? And we learned about ionic bonding. It's very strong bonding. And how do we calculate that number? We got that from the lattice energy. The lattice energy tells us the ionic bond strength. So you can see those numbers are 400 to 4,000 kilojoules per mole. They're big numbers. They can be up in the megajoule per mole magnitude because ions attract each other strongly in the solid state. Then we have covalent radii, covalent forces. And covalent forces are covalent bond strengths. These can also be very strong. And they are typically 150 to 1100 kilojoules per mole. Some of these are very large. For example, the carbon-carbon covalent bond strength in diamond, or the silicon-silicon bond strength in solid silicon. These can be very strong. Carbon-carbon double bonds and triple bonds, they can be very strong bonds. And then we have metallic bonds. These are the forces that hold metals together, from the electron C holding all those nuclei together in the solid state. And of course, as we go to the middle of the periodic table, there's more valence electrons available in the valence band of the solid, like we learned about. So these are also very strong bonds, comparable to covalent and ionic bonds. 75 to 1,000 kilojoules per mole. And for example, in metals and in alloys, these are the forces that are operative. They're very large numbers. So these are the intramolecular forces, the forces within a compound or material. Now let's look at the non-bonding forces. These are the truly intermolecular forces, the forces between bonds. I suggest that if we look up here, this slide and this slide might be worthwhile for you to print out, because we'll use these forces and their relative magnitudes to discern the properties of materials later on. So you'll use this when you do problem solving in ALEX and in recitation session, as well as on your exam. So let's look at the magnitudes of these forces. And their relative forces go from top to bottom. The highest in the table, the top line in the table, the ion dipole force, is the strongest. And then it goes down to the bottom. At the bottom are London or dispersion forces, which are the weakest forces. So we can see what the relative magnitudes are for all these. First up, we have what we call ion dipole forces. This is when an ion can interact with a dipole. And an example of this would be when a salt dissolves in water. Water, as we learned earlier when we were looking at VSEPR structures, water has a dipole moment. And that dipole moment helps to break up salts when you put salts into water, because the ions can interact with lots of little local dipoles from the water molecules. So these are permanent dipoles in the molecule. The charge interacts with it, and the energies of these interactions can be comparable to the low end of the covalent interaction scale. They can be 40 to 600 kilojoules per mole, depending on the ion and the dipole. Of course, if you have a smaller ion like lithium, the interaction energy can be significantly higher. The next strongest force, and an extremely important force in biology, is the hydrogen bond force. This is any time we have a polar bond to hydrogen, and this occurs when we have nitrogen, oxygen, or fluorine bound to hydrogen. Then nearby molecules can have interaction between their nitrogen, oxygen, or fluorine, the negative end of their molecule, with the hydrogen atom that's bound to a nitrogen, oxygen, or fluorine. And classic examples would be water, because water has an oxygen atom in it, and that oxygen atom can interact with nearby hydrogens. Ammonia shows this behavior. So we have a nitrogen that can interact with nearby hydrogens. And hydrofluoric acid is another classic case. The hydrogens on an adjacent molecule can interact with a fluorine on another molecule by this hydrogen bonding force. These are typically in the 10 to 40 kilojoule per mole range. Then we have dipole-dipole forces. Dipole-dipole forces occur in any polar molecule. So the positive end of one dipole will interact with the negative end of another dipole, and those forces will hold the liquid together. Those forces are smaller than hydrogen bonding. They're in the 5 to 25 kilojoule per mole range. Next up, we have ion with induced dipole forces. These are typically relatively weak. These are weaker than the first three. These occur when you have an ion interacting with a non-polar molecule. An induced dipole is a temporary dipole. An induced dipole is a temporary dipole that occurs on a molecule. So if you have a non-polar molecule and you bring an ion nearby to it, it will cause the charges in the non-polar molecule to begin to polarize. So the example here is shown when iron 2+ interacts with a molecule of oxygen. Oxygen, of course, has no dipole moment. But as it comes near to the iron 2+, the electrons on the oxygen are slightly attracted to the positive charge on the iron, thereby pulling the oxygen electrons to one side of the molecule and leaving the nuclei more bare on the other side, so creating a temporary dipole. But these temporary dipoles fluctuate, and they don't last long. They're not like permanent dipoles. The next weakest force is the dipole-induced dipole force. This occurs when a nonpolar molecule gets near to a polar molecule. So again, the nonpolar molecule can polarize, in the presence of a polar molecule, but a polar molecule has a much weaker electric field force than an ion does. Therefore, the net force is weaker in the 2 to 10 kilojoule per mole range. And finally, the weakest force is what's called the London force, or the dispersion force. This occurs in non-polar systems. So when you have a non-polar molecule or a non-polar atom like a noble gas, they have no net dipole moment. But we know that the electrons are moving all the time. And so there can be temporary, what we call instantaneous dipoles. It's like waves moving in the sea. The dipole forms and disappears and forms in the opposite direction and disappears. So it fluctuates. These weak fluctuations can induce weak fluctuations in nearby nonpolar atoms themselves. This becomes a cooperative interaction. And we'll see how this manifests itself later. These are very weak forces, on the order of 0.05 to 40 kilojoules per mole for very large nonpolar systems. Now let's look at this table overall. There's a hierarchy of forces. So ion dipole forces only occur in systems that have ions in them. But systems that have ion dipole forces may also have dipole-dipole going on, or ion-induced dipole occurring, dipole-induced dipole, and dispersion forces. So dipolar molecules also have small fluctuations in their charge distributions, which can increase or slightly decrease the magnitude of their net dipole moment. So this hierarchy shows us at the bottom, every molecule displays dispersion forces. So as the higher up you go in the table, these become more exclusive forces that only occur in rare systems. So what we're going to look at is systems, and we're going to identify the strongest force that operates in a system. And we'll do that when we get to our mechanics videos. Here's an illustration of polar molecules and their dipole-dipole forces. In the solid state, the molecules are rigid, and the dipoles tend to align. In the liquid state, they begin to warm up, and the molecules now have enough kinetic energy that they can overcome these intermolecular forces, and they begin to bounce around. So the positive poles of one polar molecule attract the negative pole of another, but that interaction can be sufficiently weak that at the temperatures above the melting point, then the molecules can overcome those forces. So what we see here then is an illustration of the effect of this dipole moment. So this is the dipole-dipole force on the boiling point of various liquids. Here's a series of substances, all with similar molecular weights, going from propane on the left to dimethyl ether, methyl chloride, acetaldehyde, and acetonitrile. For each of these molecules, the dipole is listed. This is in dBi times 100. And you can see that going from left to right, the blue bars increase, and you can see the dipole moment increases going from propane over to acetonitrile. And correspondingly, you can see that the boiling point tends to increase across this range also. Next, let's look at hydrogen bonding. Hydrogen bonding is possible for molecules that have an H atom covalently bonded to nitrogen, oxygen, or fluorine. Hydrogen bonding occurs for molecules that have a hydrogen atom covalently bonded to nitrogen or oxygen or fluorine. Nitrogen, oxygen, and fluorine are small, high electronegativity atoms. They tend to pull electron density towards themselves. They concentrate that electron density, making that end of the molecule negatively charged. Hydrogens that are attached to that have lost their electron density and thus become positively charged. An intermolecular hydrogen bond is the attraction between the hydrogen atom of one molecule and a lone pair on the nitrogen, oxygen, or fluorine atom of another molecule. And we draw the lone pair, but it's really driven by the overall electron density around those highly electronegative atoms. So they're small, high electronegativity atoms, so the force becomes significant. The hydrogen atom can get close to this small atom, which has a substantially higher negative charge. Here we see the manifestation of hydrogen bonding on the boiling point of a series of liquids. And let's take the top line in this graph. So we have on the y-axis is the boiling point, on the x-axis is the period of the periodic table. So we're looking at the second, third, fourth, and fifth periods of the periodic table. So for the red line, for example, we have water. That's the period 2 hydride. Then right below oxygen is sulfur, so then we have hydrogen sulfide right below there. And then period 4, right below sulfur, is selenium, so we have hydrogen selenide. And then right below selenium in the periodic table is tellurium, so then we have H2Te, that's hydrogen telluride. And what we notice is a kink in this. So the boiling point tends to increase as you go from period 2 to period 3 to period 4 to period 5. Why is that? Well, the atoms are getting bigger. It turns out their dispersion forces are increasing. But if we look at this system, you can see water is way high on the boiling point scale. There's a kink there. That tells us that there's some other force, some unique force that occurs with water that doesn't occur with H2S, H2SE, or H2TE. And we see the same thing with the green line. That's the halogens. Hydrogen fluoride has an anomalously high boiling point compared to hydrogen chloride, hydrogen bromide, and hydrogen iodide, which show a normal increase as you go from period 3 to 4 to 5 as the atoms get bigger. Ammonia shows the same thing. NH3 has an anomalously high boiling point relative to pH3, relative to ASH3, relative to SBH3. And the common names of those molecules are ammonia, phosphine, arsine, and stibnine. And so we see those three molecules, H2O, HF, and NH3, have unusually high boiling points. And those are in groups 17, 16, and 15. Now let's go to group 14. That's got methane, CH4, silane, SiH4, and germanium hydride and tin hydrides. And you can see there, we see a nice progression. There's no anomaly there. Methane has the lowest boiling point. Tin 4 hydride has the highest boiling point, and it continuously increases in a smooth function. So what is the origin of these three anomalously high boiling points for water, hydrogen fluoride, and ammonia? This is driven by hydrogen bonding forces. And we see hydrogen bonding forces all over the place, but this is more of a dramatic illustration of this effect. Next, let's look at polarizability and induced dipole. We discussed this earlier. So if I have a molecule that is not polar, and I bring an electric field near to it, so I put charges nearby it, it can induce a distortion in the electron cloud of an atom, ion, or molecule. So if we have a nonpolar molecule, this creates what we call a temporary dipole moment. That's that instantaneous dipole that appears, but then can disappear. And as the molecule moves, this dipole can fluctuate. For a polar molecule, this electric field can enhance the existing dipole, making it slightly larger than it would be. The polarizability of a particle determines how strong this induced dipole effect is. This polarizability of a particle is the ease with which its electron cloud is distorted. So let's think about two different atoms in the periodic table. Let's go back to group 18. So the noble gases, the smallest atom we have is helium. Towards the bottom is a big gas that's a noble gas, and that's xenon. Xenon is a much bigger atom, and it has a lot more electrons around it. Which molecule or which atom do you think is more polarizable, helium or xenon? Xenon will be more polarizable. It's much larger, and it's much squishier and much easier to deform the electron cloud around it. So we see that smaller particles are less polarizable than larger ones because their electrons are held more tightly. They also tend to have fewer electrons. Polarizability increases down a group because atomic size increases, and larger electron clouds distort more easily. Polarizability decreases across a period in the periodic table because of increasing effective nuclear charge. Cations are smaller than their parent atoms and less polarizable. Anions are larger than their parent atoms and more polarizable. When atoms are far apart, they don't influence each other, but when they get close by, they can begin to polarize one another. When atoms are close, the instantaneous dipole in one atom induces a dipole in the other. And this can result in a cooperative effect throughout the sample. So these dispersion forces, or as we've called them, London forces, arise when we get an instantaneous dipole in one particle, which induces a dipole in another nonpolar molecule, and then there's an attraction. It's a short, fleeting attraction, but there still is an attraction. Dispersion forces exist between all particles, increasing the energy of attraction in all matter. Dispersion forces are stronger for more polarizable, or as we know, bigger particles. In general, larger particles experience stronger dispersion forces than smaller particles. And here's our example. We can look at the boiling point for a series of substances, and we're looking at the molar mass of these substances. Let's look at the one on the right first. That's our noble gases. Those are very easy to see. We have helium, neon, argon, krypton, and xenon. Helium is the smallest atom, and you can see its boiling point is only 4.22 Kelvin. So it's a very low boiling point for liquid helium. Liquid helium boils quite easily. Then neon has a boiling point of 27.1 Kelvin, argon at 87.3, krypton 120, and xenon 165. You can see the boiling point goes up. And the boiling point has increased because the London force has become much larger for xenon than it is for helium. The same thing happens one group over in the periodic table. Group 17, the halogens, we see fluorine, chlorine, bromine, and iodine. Each of these is a non-polar molecule. These are purely covalent bonds. Therefore, the interaction between two fluorine molecules that are nearby, for example, will be the interaction between two non-polar molecules. They have no dipole moment, but they do stick together. At low temperatures, when we get near to the boiling point, the liquid can begin to form. We get below the boiling point, and the molecules will now adhere to one another. And they're sticking together because of these London dispersion forces. And the forces increase as the size of the molecule increases. So as we go from fluorine at 85 Kelvin to chlorine at 239 to bromine, which is a liquid at room temperature, 333 Kelvin, and iodine is a solid at room temperature, its boiling point is 458 Kelvin. And these all increase continuously as the molar mass of the molecule and the size of these molecules increases. Molecular shape can also affect this. So here we have two different molecules. We have pentane, which you learned about earlier this semester in naming compounds. That's C5H12. It has a boiling point of 36 degrees. And its companion molecule, neopentane, which is also C5H12, is a rounder molecule. Pentane is more like a sausage, and neopentane is more like a meatball. And the rounder molecule has fewer points at which the dispersion forces can act, and so its boiling point is lower. This table helps us to discern what the strongest forces that interact in a sample. So we start off at the top, and we have interacting particles, which may be atoms, for example, in the case of noble gases, or molecules, or ions. So if there are ions present, if there's only ions, of course, that's ionic bonding, and so that's really an intramolecular force. So that's something a little bit different. But in the case where you have ions and polar molecules, the strongest interaction is an ion dipole force. If we have ions present, that's on the red side of our table. If we have no ions present, that's the green side of the table. Then we can look at our molecules. We'll have made a Lewis dot structure. We'll have made a VSEPR shape. We'll have assessed whether we have a dipole moment or not. If we have a dipole moment, then we can classify them into two groups. On the left green box, we have polar molecules. And if we have polar molecules, we know we'll have dipole-dipole forces. If within those molecules we have hydrogen that is bonded to nitrogen or oxygen or fluorine, then we also have hydrogen bonding, which is the strongest force that's going to occur for that system. If we have only nonpolar molecules, we'll have dispersion forces. If we have a mixture of polar molecules and nonpolar molecules, we can have dipole-induced dipole forces. And of course, with hydrogen bonding, dipole-dipole forces, and dipole-induced dipole forces, we always have dispersion forces, but they're not the strongest, they're the weakest.